Welcome, everyone. Welcome to the Harmony Hackathon panel session. I'm very excited today. It's easily my favorite panel to talk about security and privacy, but also mostly with really feel good people, some of them my friends in this space. Today, I want to introduce each of the speakers just briefly, but most of all, I want to go deep on a question that I do know each of them care a lot about. So without further ado, just want to say welcome. I'm not going to say a lot about the background, even though I read each of your resume in detail and each of your hub profile and follow you on Twitter and what's not. So why don't I start with Drill? Because we've just really finishing our campaign as well. Drill, go ahead.
Cool. Yeah, I guess a bit of background on myself. I'm the founder of Webb. We're building a cross-chain private bridge protocol. So a way for you to both, right now at least, move assets across chains privately. And in the future, we're going to move on to different types of data applications so that you can prove statements about data across chains privately. And yeah, we're just very interested in privacy and zero knowledge. It's sort of the bread and butter of what we're made of. I'm excited to be here, and yeah,
absolutely.
Thanks for having me.
Yeah, it's really wonderful that Drew actually also a University of Pennsylvania alumni, that he said he's as much of a coder, engineer, but he chose to study math. He ended up like playing with so much of cryptography anyway. It makes sense.
Yeah, it's so funny. I started a PhD primarily studying mechanism design and game theory, and I dropped it because, at least one reason, I wasn't doing enough cryptography work. So glad I can say I'm doing that now. It feels like I'm doing my own little PhD through this project.
Yeah, no doubt. Just to go a little bit deeper, Drill also help so many machine learning projects as well as other consulting in the when still in Philadelphia and like New York area. That I think getting early into the whole startup scenes, learning how to fundraise, learning how to curate community, obviously understanding the mechanism design for tokens. I think it really shows. Now that he really have a DAO and a community and a forum called Commonwealth. And I just saw the DYDX announcement. Maybe you can say a little bit.
Cool. Yeah, so I'm also one of the co-founders of a company called Commonwealth Labs. We're an incubator. We invest in founders and we incubate projects. And in the past few years, we've been building a governance forum for communities in the blockchain space. So you can check us out at commonwealth.im. We have the web community there, and the Edgeware community, which we formally started. And yeah, we've been onboarding a lot of new communities. Project is led by my co-founder, Dylan Chen. But yeah, so we've onboarded DYDX, and I believe there's a few also, continuous big announcements coming in the near future. But yeah, if you're interested to get involved or stay up to date in these communities, just check the website out. It's a
Absolutely. I'll come back. There are so many themes, and I follow your GitHub more than even my own project on GitHub. So we'll come back for it, right? Today really is not me talking as a host, but really want to take some stories, most of all the work and the research you guys do. Maybe I'll jump to Dionysis to really talk about how things are in Greece and what are the new plans in Bay Area for you.
Yeah. Thank you so much, Stephen. So my name is Dionysis. My own background is that, my training is, let's say, in software engineering, but the last 5 or 6 years, I've been doing research in cryptography. Recently finished my PhD from the University of Athens with Aggelos Kelias. And I'm very interested in the topics of interoperability. My PhD was on cross-chain protocols, on trustless cross-chain protocols. We developed NepoPows, non-interactive proofs of work, to communicate between proof of work chains. And now, in collaboration with Harmony, we are working on some new protocols on proofs of stake to allow for the creation of superlight proof of stake clients that are just logarithmic in the communication complexity, but also the interoperability with proof of stake chains in a trustless manner. And so that comes into that application. So I'm very excited about this paper that's coming up very soon. And about my future plans, as Stephen said, I have plans to move to the Bay Area in October if COVID allows. And I'm starting as an incoming scholar at Stanford with David Tse's lab at the Electrical Engineering Department, where I will be focusing on core concepts of consensus, core topics in consensus, and the security performance trade-offs in the consensus layer. So this summer I've been honored to work a lot with Harmony and spend some time looking at their wallets. We also wrote a paper called Hours of Horus that I think we'll have the chance to speak about today, in which we discuss some a little bit more exotic ideas around wallets. So it's been a very exciting time. It's a good time to be in blockchain related research.
Absolutely. Not exotic at all. We call it the keyless security and wallet. I think what's exciting is Dionysis is just a very cool person, a pilot, really a well-traveled person. I can't imagine flying plane and really thinking about cryptography in the sky feels like. Most of all, Dionysis is also having another group of researcher called a common prefix. It's crazy that you guys have a common name in the Commonwealth and common prefix to think about more about DAO way of thinking about security research, cryptography research. Dionysis is also really thinking about very broad from all the base consensus layer all the way to think about all the even logarithmic space mining. But I was most impressed by one of his papers that actually have lots of benchmarks and actually playing even with the bytecode and how to optimize for the gas fees. That's how he and I connected, right? It's not just about theoretical research, but how to bring it to production. Maybe you can say a little bit about the logarithmic result that you guys achieved.
Yeah. So logarithmic space mining is a paper that we recently put out on ePrint, and I'm actually happy to announce that it was accepted to this year's CCS conference.
Wow,
so that's some good news. Yeah, it's the schedule is not out yet, but it was just accepted there, and it's a very exciting result because we've been working on this on and off for the last 2 years. I would say it's a kind of difficult construction, and what we did there was we showed that if you have an honest majority in the blockchain system, it's possible to keep only logarithmic consensus related data in the state of everybody on the network, the miners and the wallets and all the full node participants. They can just keep a small sample of blocks instead of the whole blockchain. And most of the blockchain can be garbage collected. It can be basically thrown away unless some archival node needs to keep it. But for the consensus purposes, it's not necessary. And so we developed the methods to do this kind of garbage collection. It's a protocol based on NepoPaus. It's an extension of NepoPaus and the idea of superblocks and such. And it had some difficulty in the mathematical proofs of showing that this is both succinct and secure. So we had to develop some new tools for treating the stochastic nature of blockchains that were not available in our usual models of the Bitcoin backbone and such. So we build on top of Bitcoin backbone some new set of tools. In practice, what this means is that if a miner wants to boot up and start mining blocks, and I don't mean SPV mining, I mean full node mining where every transaction is confirmed, then this miner can synchronize quite quickly using these ideas in this protocol. And while these ideas may not have a huge impact right now, as the blockchain grows with time and for the next decades to come, the space savings and communication savings that we offer will be significant because it's the asymptotic nature of these savings that is really shining as time goes by. Yeah, so that's the latest paper that we have out. And this is with Angelos Kayas and Nikos Leonardos, two of the authors of the Backbone paper, Bitcoin Backbone.
Well, congratulations. And I definitely don't think it's next decade, but next quarter. Like many of the chains are already dealing with the state explosion problem. Many actually got stuck, and actually we are struggling with the state saying how to think about not just mobile clients, but like something like a wallet that actually be able to bootstrap without thinking about all these states, right? And there's a reason. I hope that Drew and you can follow up to think about the cross chain, the bridge. I know Drew spent a lot of time thinking about it, but let me follow up on that part because I definitely want to bring the last guest, Everett, to talk a little bit about himself. Because as you guys know, I did serious research about my speaker, if not each project, but I couldn't find anything about Everett, his personal bio and stuff like that. Maybe you can say a little bit about yourself.
Yeah, sorry, I'm kind of a ghost on social media because I gave it up. I don't know, maybe 8 or 10 years ago, and I just haven't produced anything since. So it's pretty hard to find anything about me. But yeah, I was studying for the PhD at University of Illinois a while ago, and ended up dropping out to work at Runtime Verification, which is the company I'm here representing. We do formal verification and security audits for blockchain clients, basically. So a little bit different than the notion of verification in the zero knowledge world, which is focused on verifying that another computer ran a computation faithfully. Instead, it's focused on showing that a computation has certain properties that you want to be true about it. So think like, my optimized version of algorithm X actually faithfully implements algorithm X, as opposed to saying that computer over there faithfully ran my optimized algorithm X. So that's kind of what we focus on at Runtime Verification. And we use that for doing security audits over a wide array of blockchains. We're kind of blockchain agnostic. So we try to build up expertise in whatever blockchains we're getting demand for security audits in. And we use our own internal tooling to develop those capabilities. Basically, we have a way of specifying a formal mathematical model of a given blockchain language, like of the EVM or of WASM or any of these things. You can think of this as like a Coq model or an Isabelle model if you guys are familiar with those tools, but we don't use that in particular. We have our own mathematical formalism that is well-founded. And yeah, I mean, this is a great way to catch many tricky bugs because you can't lie to an automated theorem prover, right? So if you try to get the automated theorem prover to show that a given function is functionally correct and it's correct except in one case or something like that, the prover will come back and say, it looks good except here's a case where it's not good. It might be a reentrancy attack, might be something else. So it's a really good way to make sure that code is going to behave as you expect, and to define and to provide well-defined interfaces to code, which is speaking a little bit to interoperability, because you have to make a specification of what you expect the code to do. And that specification serves as kind of an API for using that code. So now you can treat it like a black box and just assume, okay, because we've verified that the code meets this specification, I don't have to actually look into the implementation details. I can just use that specification directly. So anyway, that's kind of a ranting ramble about what I do. Let me know if you have questions.
Yeah, great context. It's a great reason to stay off Twitter, if not Telegram.
Yeah.
And to go so deep with a formal verifier.
Yeah. Well, I've seen how I've seen the quality on Twitter or whatever, and it just seems low. So I don't participate in that. So
I really respect that. Being the CTO of one of the hottest, but also one of the most fundamental research project onto the whole blockchain space is so amazing a role, but also the scope of the work that you do. My PhD thesis is also on security protocol verification from compiler programming language perspective. I couldn't find your PhD topic. I only saw the publication that you have, but I do know that you and I actually have similar research interests. I was verifying the Java virtual machine back in the time for my PhD thesis. Now that you have done the entire EVM in K, it's just a really great foundation for the whole industry.
Yeah. I kind of I was convinced I was going to go into academia, and then some some personal life matters meant I had to take a semester off, and I started working at Runtime Verification and realized, oh, hey, actually, working in industry is kind of more my pace. So the publication stopped. We are still doing a lot of kind of fundamental research in how to make verification scale, especially, and because this is, the blockchain industry is the first industry where formal verification actually scales at a commercial level, right? In the past, when you wanted to do a large formal verification project, you almost certainly had to get basically government grants or government funding, and you needed multiple years to do that. And now we're reaching the point where we can, do some lightweight but full formal verification for blockchain clients on the order of 6 to 8 weeks, which is really pretty incredible if you look at the historical context of doing formal verification. So it just ended up being like, I could have stayed in academia and done research on that and had to write papers and stuff like that, but papers weren't really my pace, weren't really my style. So I just kind of prefer the more engineering side of it. And all of our tools are open source. The way I see it, like we're just kind of trying to, I'm not convinced that our tools, like the K framework that we use, is going to be the future of doing formal verification or semantics, but something like it will be, and it's all about kind of advancing the field and raising people's expectations, basically saying, yes, we do expect that for high assurance systems, formal verification will be a box you check somewhere along the delivery pipeline. So
absolutely. And the great thing is with the right tools, and I think all the mathematical framework, if not type system, is already there. But within weeks, we're really dealing with tens of millions of funds, right? So the impact is really there. And I have a lot to follow up with Dionysis, and I really want to get into COD, both verifying all the way to protocols, hope maybe even about the bridge, all the way back to the smart contract with the reentrancy, if not some of the information flow. My PhD topic was on non-interference, that actually really related to many of this contextual verification. But we'll come back to it, because I definitely want you to mention just a little bit about some of the project that you help, whether the MakerDAO with the multi-collateral vault that you help. Maybe you can pick one project that to give us some sense how it was involved, what was the personal experience.
Yeah, well, we've had lots of projects, and we're not the most flashy, like making big announcements or something. We're getting better at that. It's something we're definitely working on. But I guess I can talk about the multi-collateral DAI verification project, which is probably the largest scale verification using K that has occurred to date, actually. And actually, we didn't really head that project ourselves. We just helped them. That was back in 2018, early 2019, and the folks from, at the time, DApp Hub, which was kind of the core development group of MakerDAO at the time, approached us and said, hey, how can we use your tool to verify this really large system, basically? And we kind of looked at them a little bit shocked, like, you actually want to try verifying a system that large? And they're like, yeah, let's do it. And so we had them come out and visit us for a couple of weeks, actually, and just totally for free helped them learn how to use our tools really in depth, like 8 hours a day, me sitting down with them being like, oh yeah, when you get this bug, it means that. When you get this error, it means that. So really in depth. And by the end of it, they left and were able to kind of make progress on their own with a little bit of assistance over video calls. And yeah, they came up with kind of a high level DSL for specifying the behaviors of the whole multi-collateral DAI system. And they had a tool that compiled that to a bunch of K specs. So each high level spec could get compiled to 3 or 4 K specs, basically. And then they, just set a computer grinding away at verifying these K specs, which at the time was taking like a week to run them all, because there were about 1,100 different proofs it had to run. Now we're down to like 18 hours for it to run the same proof suite, which is pretty nice. So yeah, I mean, the process was pretty eye-opening, because the biggest challenge, honestly, was with the specification language, right? You have to, at some point when you're doing formal verification, you have to write down a specification of the expected behavior of your contract, and you have to find this balance between, there's enough information in the specification that the prover is able to make progress, but it's terse enough and is kind of highlighting the correct things that the human's able to understand it and intuitively say, yes, this is the correct specification, because it's easy to prove incorrect specifications all the time, right? So that's kind of this balance that you have to find, is like not too much information to overwhelm the human, but enough information for the prover to make progress. And I think they did find that balance. They found a really nice language called ACT that they use, and it's kind of specific to the EVM, but it ended up working out, and they wrote all the specs down and we got them all proven. So that's kind of a cool project. Yeah.
Well, I'm glad I asked for the story. I read quite a lot about your blogs, as well as follow many of your announcements. But like really knowing how that works among the people and get the two teams together is just incredible. With that, let me jump back to Drill to ask even the one question that I have in mind, right? And I think that will set the tone to know from the engineering perspective that Drill is working on like both EVM as well as Rust and Substrate these days, all the way back to some of the theory and research that will cover at least some topic. To me, is very fundamental about the security and the privacy for hopefully the years to come. Maybe Drill, I asked you the one question even on the Twitter, like you're working with so many projects, so many like people on thinking about the engineering aspect of bringing the best cryptographic primitives and later on privacy across chains. How have that experience informed you about the engineering aspect and the production aspect?
Yeah, definitely. And it's a good question, and there's a lot of different answers. So I'll like try to pick a few. I might go on a tangent. But so something I even spoke about at ECC that is pretty apparent so far as we've been building out these bridges is that Ethereum is your constraint. And so it's somewhat similar to like the weakest point in the system is the constraint of the system. I guess in this case, you can say the function out, like the part of your bridge, the chain on your bridge that has the least amount of functionality is the constraint you have to meet. So like on Solidity or on the EVM, for example, you only really have right now one elliptic curve that makes sense at this current moment to build zero knowledge applications with. So when we even move to Substrate or we move to these Rust-based or WebAssembly-based blockchains, it's definitely more expressive. We can do as many things as we want because a tremendous amount of software compiles to WebAssembly. But if we want those systems to be interoperable with Ethereum and with EVM chains, we have to use the tools that work on the EVM. So this is something we've actually, we just got working pretty recently. We have like the same hash function implementations that work on Ethereum and Circom working now in Rust. So we can deploy applications to any Rust-based blockchain and have at least the data we expect to work well or interoperate well. This will allow us to now build like full-blown protocols on top that can speak and understand one another between EVM chains and Substrate chains, maybe as well on Near and Solana in the future. But yeah, overall, it's very nice to be working with Rust and be working with a much more expressive environment to build applications. But there's many more decisions you now have to make. That's something like the EVM sort of really constrains you to.
So I have so many questions to ask, even just on one topic you open up. But maybe to make it interesting, if not at the deepest view, right? In a year, what would be a good indication whether we have gone down the right path and keep going with Solidity, or the whole industry should move to like WebAssembly and Rust?
Yeah, what would be, very good indicators from the Ethereum side is hopefully we get at least one new precompile for a stronger elliptic curve. That would be really cool. And I think maybe there are ways and there's added functionality that you can kind of hack together to verify certain proofs through Starks. So maybe you can sort of verify different proofs on other elliptic curves that are not supported on Ethereum using Starks. I'm curious. I don't know a ton about it, but I remember reading that Mina was looking to sort of offload their bridge protocol, or at least some light client protocol on Ethereum by using a Stark proof. So maybe this is sort of like a middleware in some sense for things that don't exactly work on Ethereum. But yeah, added support for curves on Ethereum would be, I think, the most impactful thing. Especially, I guess people are talking about BLS 381 in anticipation of the ETH2 launch. And I think we shouldn't make too many like expectations, because governance is really a very slow process. And especially in a project like Ethereum, it's not even clear who at the end makes these types of decisions.
Wow. I actually would encourage the other two guests to ask a question, because it shouldn't be me having ideas about this. But I want to ask one more first myself. You really work with so many different projects to really make cross-chain happen, right? I like the fact that you are not making a philosophical argument, right? It's not about which language you like the most, or which ecosystem, or which project you are betting on, right? You are saying some of these primitives and mechanism has to happen, so that we can innovate more. But I would still like to pose it to be a little bit more strong personal view. So I don't like Solidity. I don't like EVM. Like I've studied virtual machine all my life. I studied language all my life, right? But there's a reason why JavaScript won. And I'm not trying to start a language war here, but because of the constraint, and I wouldn't say like it's just the constraint of Solidity, it makes the ecosystem much more uniform and much more flourishing, right? WebAssembly, Rust was a miracle, I would say, but WebAssembly is still very primitive, and try to make it uniform, to try to make everything nice. Do you see Solidity as a strong advantage to make it so simple and not like keep innovating and changing all the time? Even though Rust can be as, for sure, WebAssembly can be as atomic of building anything. There's no reason why either camp wouldn't win, right? Do you have a strong view here? Which approach even to double down on?
Yeah, it's so funny because we built so much in Substrate, and then we started transitioning to build most everything in Solidity, and are now returning to Substrate. I would say doing things in Solidity today is still easier. It's still easier to architect systems, primarily in the cross-chain space, because we all plan to deploy on EVM chains. So inter-contract calls and like the sort of access control mechanisms and governance systems that you build for EVM applications, they set the tone for what I think will implement in these newer environments. That's like exactly what we are doing. So I'm biased in that sense. We realized that architecting the system in Solidity was better than trying to architect it in Substrate. And so we are re-implementing the Substrate side as we have done in Solidity. So yeah, some bias, but I still think like the tool chain, for example, developer tools, they're more, battle tested for Solidity. The EVM is slightly more battle tested. The other thing is in Substrate, we even had some new hiccups coming up when we tried to start working on Solana. But in a lot of these new environments, there's either tools that aren't supported just because the ecosystems haven't developed them yet, or in the case of Substrate, there's a lot of freedom that the developer now has that they otherwise don't in the EVM. Certain things like computation and gas limits or a weight system, that's all pushed to the developer on Substrate. So you have to take care of, the sort of gas costs yourself, which is something that's kind of, it's a pain. People don't like gas when they're dealing with it, but that is a good constraint in some sense. So yeah, there's a lot there, but I'll leave it at that.
Dionysis, would you want to shoot a question?
Yeah, Drew, you mentioned that the litmus test, let's say, for the survival of Solidity is whether it will add support for at least one elliptic curve. So can you share what would be like your wish for that elliptic curve? What's your favorite and why?
Well, I don't know if I think if I had my true wish list, there's a precompile that was proposed a while back that would support any elliptic curve and sort of define a standard interface for people to add them more generally. For your actual question, I think everyone that I've talked to that's building on even Substrate and elsewhere are looking to use BLS 381, primarily because you can do signature aggregation through that protocol better. Although there are signature aggregation protocols for BN, but the security is less. So there is that. When we started, I was sort of one of the like ideological stances I took was that we wanted to work with non-trusted setup snarks. So I was in the beginning trying to learn more about how we could get non-pairing curves on Ethereum, such as curve 25519. But I think I've definitely changed my stance in this regard. I don't know if the more the merrier, but I would like that on my wish list.
Let's get all of them on some new chains, right? For sure. Everett, would you want to ask some question?
I guess I don't have a question, but I wanted to second something that Drew was saying about Solidity versus Rust versus other languages and stuff. And we take a very agnostic approach at Runtime Verification. So we don't care what language you write your source code in, as long as it compiles to something we can do verification with, which would be, in this case, EVM or WASM, basically. But I think that the important thing to remember about a kind of blockchain-specific language like Solidity versus a generic programming language like Rust is that, of course, the generated code from Solidity is going to be a lot more efficient, basically, than the generated code you get from Rust. So we've tried to do some verification of Rust projects, compiled to WASM, and the code sizes are just ginormous, basically, in comparison to what you get EVM bytecode-wise out of Solidity. Now that can and it has been reduced quite a bit. Like, you can do a lot of work to improve that situation. But that's one example of how having kind of a specific language for blockchains gives you an advantage. And that same parallel is reflected in the EVM versus WASM, right? WASM is kind of a blockchain agnostic, it's just a VM, right? And then you have EVM, which has a bunch of like blockchain specific things built into it. And it's it just because of that, you can make very specific calls in EVM that are a lot more efficient computationally wise, and also verification wise in our case, when we're doing symbolic execution, than in WASM, where it might take a whole entire function to do a setup and just do the same thing, basically. So that's kind of, one trade-off I want to remind people of when they're thinking about, okay, do I do Rust to WASM or Solidity to EVM, or do I try to do Solidity to WASM or Rust to EVM or something like that? There's this trade-off always in generic versus specific when doing any of these things, right? So it's not a simple question to answer, and so we just throw our hands up and say, okay, we don't care. Like, we'll do whatever language you want, as long as you have the time for it, basically. But yeah,
absolutely. I think Everett is actually opinionated about the K language. That's why. I'll jump back to Drew for one more question, because not just about EVM versus Substrate, but Drew is really care about the privacy aspect. Starting from Tornado Cash, I think finally everyone understand that it's usable not just about like just Zcash and what Bitcoin wants to do, but actually what will be a mixer looks like as from a product perspective, right? You also mentioned about NFT and other use cases in DeFi that in our private conversations. Would you want to tell about how you feel about privacy product being used in our space?
Yeah, definitely. I think most every even traditional product that crypto companies are using can be made more private today. People are building, even I guess like DeFi portfolio trackers, things that query blockchain nodes should have privacy so that the nodes themselves can't track the people who are querying them. Doing payroll, I guess, as this space gets more and more investment in stable coins and, from traditional venues and begins to pay employees in crypto, we have a huge privacy problem between, investors, employers, and employees, where our whole bank account is basically public info to anyone on this sort of path. And I think over time we'll want to build private products for doing these types of things, for doing payroll, for analyzing your portfolios and the historical performance of them, and even purchasing, art. People like to buy art. People might do so across chains. There was a lot of activity on Solana with these apes. And I think people who are at least purchasing these types of tokens, purchasing these products, should have a product that preserves their privacy when they do so. There's also another one which I should think more on it. I played games a lot when I was younger. I was a big gamer, playing like TF2 and a lot of these early collectible item games where you'd collect hats and they would become pretty valuable. And we have a lot of, I think the game market is growing tremendously on these blockchain platforms. Having addresses or having like no privacy in this is I think a bad thing for the long term, because people are going to start associating their real world addresses, say that they, maybe receive income from their employer from and play these games and build a web of data that someone else can sort of mine and fingerprint them with. And I think, at some point we as a space need to embrace privacy products a lot more if we want to rebuild the internet rather than, build the same type of structures.
Super cool. Go ahead. Yeah.
So privacy is not something I've considered very much because I'm usually focused more on code correctness, but we did have a small investigation into, how would we incorporate into a case semantics, because that's what we do, some notion of being able to show that something remains private. And one of the questions that came up is, what does the source language for a smart contract system that allows you to have both public on-chain data but also private data somehow specified in that contract, what does that look like? And we came up with a couple example snippets of just basically modified solidity where we could have modifiers over some of the data or something like that. But I'm just wondering, is that something, from our perspective, we build semantics of programming languages, and that's something I think we need to have on our horizon, is how are we going to represent that in our semantics? Is that something that the community has been thinking about much in terms of how the programmer can specify, I want this to remain private, but this to stay public?
Yeah, it's very interesting. I would say no, this is probably a pretty deep idea, but I think in order to incorporate, whether privacy is taken into account in a formal semantic, is to use zero knowledge proofs. And so in some way integrate into the program, the formal verification, some functional verifier, right? That you expect to be, say, true when it's run with this input. And this is there was actually a topic recently, someone rehashed with me, called private function evaluation, where you can prove statements in zero knowledge about someone's execution of a function with private inputs. I don't know how well this lends itself to formal methods yet, but it seems like you could define sort of a language that incorporates that type of concept.
Yeah. Yeah. So as far as reasoning about the private components go, we don't actually have to do very much of that at the formal semantics level, because we can just axiomize it and just basically say, we expect it to have these properties, but not actually specify how it goes about having those properties, which is the easiest way to deal with basically anything crypto or cryptography, not crypto like cryptocurrency. Like, for example, when we go to verify anything that has the Ketchak hash or SHA-256 or anything like that, we don't ever compute the actual Ketchak or the SHA-256. We just state some algebraic properties of it. Basically, it's injective enough. If you give it the same input, you'll get the same output. Stuff like this. We just make sure that those are stated, and we do the same thing for like the EC DSA recover precompile, for example. So from the formal reasoning perspective, it's not hard for us to deal with these things, because we basically just say we're not going to deal with it.
Right.
We're going to assume that it works correctly, basically. But I'm just curious more about, like, if I'm a Solidity developer and I want to do private payroll or something like that, how do I write my Solidity program differently to tell the compiler, this needs to be compiled to a snark circuit, but this needs to be compiled to like the on-chain EVM bytecode that gets sent there? So I don't know if there's a good answer to this question.
You could, I mean, maybe you could hack something together, but I mean, a good question for you is, have you investigated formally verifying SIRCOM programs? Or like, if you've looked at some of these Rust-based zero-knowledge DSLs, there is a program you're writing. So in some sense, you could formally verify that as if it was a public program, and use the methods that you guys use in K to integrate, say, execution of this zero-knowledge program, which has its own formally verified spec, to adhere within this larger protocol. But yeah, certainly maybe take a look at SIRCOM, because in some sense, like, that's only another gadget or program that runs eventually in Solidity or in the EVM.
Yeah. So is SIRCOM, just a couple of questions, is it specifically just for compiling ZK snark circuits, or does it also produce like EVM bytecode that handles the public component?
Yeah, the developer writes a program and compiles that into a verifier Solidity file. Okay. And in between that process, you generate a proving key and a verifying key for the target snark. It's a tool.
Exactly what I was asking about. So thank you.
Yeah, it's built by Ident3, or formerly like the team who's now running Hermes, recently acquired by Polygon.
Cool. Dionysis also have interest in privacy.
Yeah, and actually on this discussion, I want to maybe come back to the question that Everett mentioned. I think that's super interesting. Like, how do you develop language with semantics that allow both public and private information to be indicated and expressed in a smart contract language? And I think the hope that Everett expressed here, that we could maybe modify Solidity and add something like a visibility modifier instead of private, have something like really private, and that would be hiding things. That kind of hope is maybe a little bit too grand. I think that would be impossible to do in this generic way, because generic smart contracts with privacy are impossible. And the reason is that in a publicly verifiable way, I mean, you don't require the participants to be online all the time. Like, you can rely on the miners for that. But in a private smart contract where everything is private, some of the private data is kept off the chain, right? All of the private data is kept off the chain. So the people that have these data, they need to contribute to the circuit so that the private function is evaluated. So in case people go offline, I mean, you have to have some recovery mechanism, and then this is a balance between safety and liveness there. So it's difficult to do it generically. There is a very recent work by Thomas Kerber. He's a student at the University of Edinburgh, called Kachina, Foundations of Private Smart Contracts. And there, in this paper, it was published just this year in the Computer Security Foundation Symposium. And there he explores the foundation of private smart contracts and really the boundary of what is possible and what is impossible. And I think that could be used as a foundation to see how we could modify a language to add these modifiers, and then also to see, what kind of limitations there exist in what can be computed privately and what cannot be computed privately. And maybe we need to do some more exploration on how we can change the language a little bit more broadly than simply taking Solidity and hoping that we can do it in a very, very generic way.
What are your thoughts on StarkNet in that case?
Yeah, I think it's a really interesting thing that they're doing with you mean like Starkware's work, right?
Sure. Yeah, just like generic program execution.
Yeah. I mean, they do a generic program execution, and you can take any smart contract, move it to layer 2. But then, I mean, all these data is available to the single prover that is running their carrot language and providing their proofs on chain. So you're losing privacy with respect to the prover there. If you wanted different participants to have, like, each of them to have a little bit of different private data and never that data to be disclosed to a single prover, then that might be more difficult. If you're willing to have a single prover that has all the data and has some assurances of availability, like they're doing with their prover and their availability committees, I think that's a promising direction. It's kind of taking a discount on privacy. You're saying, okay, this party will see everything, but you do have the assurance that not everybody on the chain is seeing everything. So it's a promising direction, I would say.
Sure.
Super amazing progress in the even engineering perspective. Obviously, Starkware launching all the product as well as the mainnet. But let me jump back to Dionysis now on something far, far out, right? Cryptography, Lattice, math, if not even witness encryption. I think it's time to pop it so that everyone can keep giving some ideas and even knowing what might come. Dionysis.
Yeah, so this is a very interesting primitive that has been maybe the cryptographers have been thinking about for many, many years, and it's called witness encryption. And it's this idea that instead of it's very similar to regular encryption, but it's a much more powerful primitive. And instead of encrypting for a particular key, so instead of me encrypting something for Stephen's key, I can encrypt something for a problem solution. So I can say, I have a problem in mind, and that problem could be a mathematical problem. And then I'm encrypting to that problem. So instead of using a public key to encrypt to, I encrypt to a problem statement. And then to decrypt, instead of using a private key, the decryptor needs a solution to the problem that I've stated. And that's the basic definition of witness encryption. And then to state it, let's say with a mathematical example, if you have, let's say, a problem like, I don't know, the traveling salesman problem, a famous problem from computer science, right? What I can say is that here's my graph, and I'm encrypting some data for this problem, which is this graph. And anyone who finds the traveling salesman solution to this particular graph can decrypt my data. That's the idea. And in witness encryption, if we can construct it, it's possible to do it for generically any language in NP. So any language is possible to do. And that's quite interesting, because most cryptographic primitives that we see in everyday life, like zero knowledge proofs, encryption, just regular encryption with keys, signatures, and so on, they can be kind of translated to witness encryption. So it's quite a generic primitive. Unfortunately, it's currently a kind of an exotic primitive. It's being developed over the last couple of years very heavily by the Lattice community. They've made a lot of progress. There've been several constructions out there, but it's kind of a cat and mouse game. Like they develop a protocol, then it's broken, then it's kind of patched, and then there's a new protocol coming up, and that's broken again, and there's a lot of back and forth there. So that's one thing. Like we don't really fully understand the security very deeply. It's and even though there's like very deep math in it, it's still a very, very new field. And then at the same time, it kind of lacks in performance. So because it's so generic, like this comes back to the discussion we had before, because it's so generic, it's very hard to do it efficiently for large dimensional problems. If you have a very, very large dimension, which is what is usually very useful, right? At the same time, this will take a lot of time to compute and to encrypt something or to decrypt something. And even though, like, theoretically speaking, we can show that these things, asymptotically, they behave nicely and they can be done polynomially, the constants in these polynomials are enormous. And computer science has showed us again and again that, if we have polynomiality, then eventually this will become practical. But sometimes, it takes a lot of time. But the hope is that these constructs, they will evolve over the next few years. And my personal opinion is that this will play a very, very important role in the blockchain space. And the reason that I think that is that these witness encryption schemes, they can be used to construct something called time lock encryption. And time lock encryption is something that is it has been around in the crypto space, in the cryptography space, since I think the 80s as an idea, right? And the idea there is that I want to encrypt something for the future. I want to say, here's a piece of data, I encrypt it, and it should be decrypted on January 1st, 2022. And before that time, nobody can decrypt it. And after that time, everybody can decrypt it. So that would be time lock encryption. In the initial time lock encryptions, schemes, they did something like they required some sort of verifiable delay function or some sort of proof of work. So you had to do some kind of serialized work on top of your ciphertext to get closer and closer to decrypting it until eventually, after you put in a significant amount of computational power, it would be decrypted. But this is not very satisfying, because if you have a very, very stronger computer, now the date, you can move it from January 1st, 2022, you can move it to tomorrow, even though you have to do the work sequentially, a supercomputer kind of breaks this thing. And then at the same time, if you don't put in the computational power and all the energy to that, then nobody's decrypting it and the data is forgotten. And then you have to pick it up in 2022 and then the data is moved to 2023. So who knows? It's not very accurate. But with the invention of blockchains and the idea of witness encryption, we can implement a quite accurate time lock encryption. So if we have a witness encryption, we can use the blockchain as the problem of witness encryption. So the idea here is that we say, I am encrypting something, and the problem that I'm asking is that some proof of work is found tomorrow. Okay, so I say 10 pieces of proof of work are found, 20 pieces of proof of work are found. And these are very, very predictable in the blockchain space. If my problem is that starting from the Bitcoin Genesis block, 1 million pieces of proof of work are found, this is a very predictable rate. So I can say, okay, this is the number of blocks that I'm asking, and I'm encrypting with the problem of finding these hash function values, right, that meet the target and they create a blockchain. So if we believe that the blockchain is a secure system, then this will be decryptable in a very precise date in the future, right? And then at the same time, it will not be it would not be decryptable before, because if it were decryptable before, some adversary will be able to attack the blockchain and double spend, which we believe is impossible, right? So that's the kind of argument that goes into that. And there's a lot of nuance on how to build it accurately. Like, for example, in the Bitcoin case, there is variable difficulty and difficulty adjustment. Ethereum has the same. It's kind of mining power goes in, mining power goes out. So it makes things a little bit tricky, but many, many things are possible, and it can be made quite accurate in reality. And in the case of proof of stake, in fact, it can be made very, very precise, because if you have honest majority, the blockchain grows at a very precise rate. So that's one of the beautiful things about proof of stake, that you can use it as the constituent to build time lock encryption that is really, really accurate. So I've introduced like a lot of cryptographic pieces here. It's very exciting, but at the same time, it's a little bit exotic, because, as I said, it requires a few moving parts, and one of them is witness encryption, and we're waiting for the Lattice community to make progress in that so that we can use it in practice. But there has been some progress in creating time lock encryption from witness encryption. So we know how to do that. If we had witness encryption, we know how to do time lock encryption. And using some of the lattice-based constructions, there have been some toy constructions of time lock encryption on top of proof of work blockchains. So, and they work in reasonable time frames. So you can do a time lock encryption and do the encryption, in a couple minutes for some of these toy examples. And so this is really promising. And I hope that the community will start looking into that a little bit more. Because time lock encryption can be used for so many different applications, and now the blockchain is making it possible. So this is maybe my bet for the future, that this will become a very important part of blockchain systems as we go forward.
Yeah, I don't think it's exotic. That is impossible. I strongly believe it's going to be before quantum computing on blockchain, that lattice and witness encryption and time lock will happen in our lifetime for sure, hopefully in coming years. I know you guys are all mathematicians and also theoretical scientists that can ask lots of questions, but let me bring back to one topic that each of you can maybe ask something very, very specific, if not relevant. We want to ask Dionysis to use all these ideas back to wallet security. Maybe Dionysis just help draw the connection, why this primitive will be so amazing if we can actually do many of the wallet transaction and authorization using that primitive.
Yeah. So that's one of the very, very interesting applications of time lock encryption using blockchains, because you can build some primitives that are truly like what we call crypto economic, right? Where you can combine cryptography and economics, and not just in some imaginary fashion, but they are very concrete terms in a probabilistic equation where you really have like some term which is cryptographic, and then addition, and then some term that is economic. And this gives you some very, very nice assurances about how these systems will work. So in terms of wallets, that's one of the very interesting applications. One of the things that you can do is you can build keyless wallets. That's something that we call keyless wallets. It's a kind of new primitive in blockchains. And the idea is that the user does not have any key material on any online machine, right? So there's no secrets on the machine. The machine is booted up, it's just brand new, and the user can just simply enter something like a password or an OTP code from an offline mobile wallet, right, or a mobile device, and that mobile device is completely air-gapped, and that piece of OTP, it can be very short. It can be like 6 digits long, and yet this would allow them to spend their money. So it's kind of if you describe this to a person who uses blockchain for the first time, they would be startled. Like, how is this possible, right? You can guess that. If it's just 6 digits, you can just brute force that. But with the use of time lock encryption, you can implement something called an on-chain brute force protection or a rate limiting scheme, where it's impossible to brute force these things. And so the basic idea with this OTP scheme is that what you do is you pre-create, when you create your wallet and when you place your money in it, you create a sequence of OTPs for the predictable future, let's say for 2 years or 10 years. And then what you do is you encrypt each piece of OTP for a different date in the future. So you say, okay, this OTP is for 1 hour. This OTP is for 2 hours in the future. This one is for 1 year, and so on, right? So you've got maybe even 1 million pieces, right? And then you place all of these in, you publish all of these. You can put this on IPFS, whatever, right? And you organize them in a Merkle tree, and you put that root into a smart contract. And now what the time lock encryption allows you to decrypt these pieces of these secret pieces anytime the blockchain has grown to a particular length. So these pieces of data are decryptable by anyone, really, anyone in the public. But the person holding the OTP wallet on their offline mobile, they know the OTP code slightly before the rest of the network. So what they can do is that they can reveal their knowledge of that OTP maybe 1 hour prior. So the way that they do that is they do a commit reveal scheme in which they commit to the hash that they know with a salt, right? And then later they reveal what they knew, and they show to everyone that this is actually what everybody else decrypted, right? And now they have been proven to be the rightful owner of the money. And notice that during this process, like, no secret data was in any online device, right? The only online thing that remained secret was just the salt that was generated during this 1 hour period. But this was created by the machine that was booted up anew, right? So there's no secret key material there. No signatures, nothing, right? And the security of that really stems from the fact that you don't have any blockchain reorgs that are very, very deep, right? So as long as you don't have that, you can be assured, you can rest assured that nobody else can spend your money. So this kind of gives new direction in usable security, because now you don't have to take care of private keys. You just have your offline little device, and all you do is enter your password. You don't need to maintain a device that has secrets. You can do it even on a new computer, right? As long as that computer is secure at the moment that you enter your password, you're fine. But if it's compromised in the future, you don't care, right? It's just that this 1 hour that I use this computer, I need it to be secure, and that's all. And that's how you could build keyless wallets using OTP passwords. And if you think about it, if you have time lock encryption and witness encryption in a way that it has the properties that we suspect it should have, then any attempt to spend this money would require an adversary to commit to the blockchain before the revelation date, right? And so the adversary could try to brute force it, but if it's just 6 digits long, 6 like decimal digits long, they would have to make 10 to the 6 attempts. In a cryptographic sense, this is very, very low, right? But in an economic sense, this is quite large. And an adversary that needs to do this many attempts, they need to record every attempt on the real blockchain, which means they need to pay for gas fees for all of that. So that's like 10 to the 6 gas times the gas of each transaction. That's like millions of dollars, right? So that wallet is economically safe against any adversary who is rational and is not willing to spend millions or tens of millions to steal from your wallet. And then if you want to make it even safer, you can add an artificial cost in every spend. You can say, okay, every spend costs a little bit more money. And so there is this balance between cryptography, which is like the secret from the salt and the hash that has like 256 bits of security, and then the economic part, which is like 20 bits of security. It's very low, but that number of bits corresponds to real money that you have to spend to do the attack. So this attack is really against an adversary who, on one hand, is a polynomial adversary, so they cannot break cryptography, but on the other hand is also a rational adversary, so they don't want to have a negative expectation in how much money they need to spend. And that can be nicely summarized in an equation. And with Harmony, we developed a paper on all these concepts called Hours of Horus, keyless cryptocurrency wallets, and it's actually private, or it's public. It's a public paper on ePrint that was published very, very recently. So you can take a look at that, and it will be under submission in an upcoming conference. So that's really exciting. And one of the really weird things about it is that you cannot, in contrast to any other smart contract where you can execute it in a fake chain that you grow on your own, these things you cannot do it, because you would need to put in the real proof of work or the real proof of stake to get any results. Otherwise, you don't get anything, right? So if you fake it in a testnet, you cannot really get away from the rate limiting. The rate limiting is applied on the real chain that has the real proof of work or the real proof of stake, and it's making progress. So that's one recent development that I'm very excited about. And I think these kinds of applications will drive the cryptographers behind Lattice cryptography to really, really work on these, because it's one of the first very, very practical applications that we see on blockchains. And I think it's really cute that it combines a lot of different primitives. It combines time lock encryption, witness encryption, but also commit reveal and having some prior knowledge, as well as the concept of blockchains, where you rely on it for a lot of things. You rely on it as the encryption or the decryption key for the witness encryption, but you also rely on the blockchain for the common prefix property, that you don't have a reorg in the chain that is very long, right? So I think that's a very, very interesting development and advancement in wallets, and I'm hoping to see this make progress and eventually implement it. That would be really exciting.
Absolutely. Keyless security, keyless wallet, as exciting as it gets. I can easily see 10 papers on this already, but also actually a product that I love to use. Hopefully, you guys will all stay around for to talk about wallet security. But I want to jump into one last topic with Everett about programming language design. You must be also as much of a compiler geeks, if not type system and what's not. Do you think that soon that formal verification and all this strong type system can really help smart contract developers, engineers, not asking for runtime verification to do multi-year, multi-months of development, but like, can there be a more synthetical approach? Can there be more very practical very soon? Because all these engineers are dealing with like tens of millions to deploy.
Yeah, I think that we will see more systems that make it easier for developers to basically ensure the security of their system. But I mean, that one thing we were talking about earlier is how do you extend one of these languages with with privacy features? And I got some good answers from Drew on that about examples that exist now, which I didn't know about. So thank you. But there's even simpler things we can do to make it harder to mess up, basically harder to shoot yourself in the foot. And one is this idea of like a stronger type system. So a very simple example would be like a data flow based type system. I think there's several programming languages that have these permission systems and stuff like that built directly into the type system, so that you can say, this piece of data should only be usable by these fragments of code here, for example. And if there's a way that any other fragment of code can somehow get access to it, then that is a violation of the type system. And then it's checked statically at compile time. Ideally it's checked statically at compile time. And then you don't have to add any extra instrumentation to the code, which would increase the gas cost. Now, not in every language would you be able to check that statically and then not add instrumentation to the code. Sometimes you do need extra instrumentation in the code that's submitted to the blockchain to enforce that static compile time check. And that basically boils down to, how strong is your type system, and do you have like a type erasure property where you can remove all the extra fluff that deals with actually checking that type property. But I do think that we're going to see more of this type of thing become prevalent, really. I think even the Solidity language, we're seeing evolution of that to incorporate more of this. Like the first would be this work that was started by Leo Alt and other people at the Ethereum Foundation on the Solidity compiler, where at compile time, it real quickly runs basically some model checking queries for you, right? So I'm not sure if you guys are familiar, but the basics of it is, you have these assertions in your code and you want to make sure that an assertion will never be violated. So the model checker there will go and build a query to SMT that basically checks that those assertions can never be reached for you. So it's kind of a reachability query will ever be reached. And you don't have quite like 100% guarantee that the results of that are accurate, because it's still an ad hoc encoding of the Solidity code to SMT rather than actually over the EVM bytecode, but it's a really good assurance in general. So I think future type systems for Solidity that take more of this approach are a really good idea, because they're fast, they're transparent. The developer doesn't even know that their code is being model checked. They don't even know they're using model check. They might even not even know what a model checker is. But it's a really good way to kind of increase the assurance of everyone's code across the board by building things into the tool chains that everyone is using, into the Solidity compiler, into maybe Truffle, some other tools like that. And an example would be adding some sort of extension to the Solidity type system that is you could call it like a data flow extension, or you could call it like a privacy extension or something like this, where I don't mean privacy in the strong sense that you guys are discussing here with the zero knowledge, but privacy in the sense that, okay, so if you have a reentrancy attack, usually what that means is some internal contract state is leaking to some other external contract, which then is using that to make an informed decision about how to re-enter into your contract, right? And that's how you can get kind of these loops where external contracts are able to keep kicking back into your contract and take your funds. So if you were to instead say, okay, this piece of state is never allowed to leave the contract and be used somewhere else, then that would immediately be caught by the type system, that particular type of reentrancy attack would be caught by the type system, for example. So I don't know. It's hard to the difficulty is always that reentrancy is useful. Like it's a useful thing for developers to be able to access. The problem is allowing them to access it in a way where they can't shoot themselves in the foot. And that's where these stronger type systems come in, where you can let the developer express exactly what's allowed and what's not allowed. So one example of this is the newer deployment of the new liquidations, 2.0 for the maker system. They're using I think a nice like locking system for reentrancy, which I think works out pretty well. And unfortunately, it falls in this category of you have to instrument the code that goes on the blockchain to check these locks and set these locks and stuff like that. But in the context of EVM, there's not really a better way to do it. In other languages, there might be, better ways to do it to block reentrancy, but not in EVM. So I don't know. That was kind of a long-winded answer. So
not enough. I wish there are a few more hours for me to hear. In particular, all these ideas about like safety as well as like broader concurrency, right? We've been dealing with device driver memory safety back in the last few decades. I think this is really critical, right? Again, let me, as a host, ask a more provocative question, right? More like when will it be possible for someone to develop even Uniswap v3 you dealing with MakerDAO or kind of vaults mechanism right from scratch, or like worst of all, many people fork Uniswap, but then they shoot themselves in the foot, right? Not knowing changing one assertion check or one variables will have like consequence of tens of $millions of dollars. Do you see like, is it going to be like maybe even this year with model checking in the background, maybe next year when they're better programming language, if not all the way to something like Rust with linear type system and what's not? Do you see that happening next year, that people will be not asking, even need runtime verification for help, but be able to develop, maybe modify Uniswap to be able to deploy their own contract modification, but be able to like check it within hours, deploy within weeks?
My short answer is no. I don't think next year is a good target. Maybe 5 years, right? Like I could see it in 5 years that you could do this, but I think that there's somehow like a fundamental flaw in the idea of I can take some other smart contract, make some modification to it, and then redeploy it and know it'll be safe. Because the thing is, when you do that, you're changing the specification of the contract, right? And so you don't know that all the checks that were run against the previous contract hold over your new contract without rechecking them. So if they were done in a mechanized theorem prover, you can recheck them. But you also don't know, do I even want those checks to hold over the new contract? Or are there more checks that I need to put on the new contract? So I think the key here is not necessarily making verification automatic as much as, because automated verification doesn't mean anything. That's, everyone approaches when they don't have an idea of what verification is. They say, oh, can we make this automatic? Can we make this No, it doesn't make sense, because you have to still write down at some point what you're verifying about the code. You have to write down the specification of what you care about. But I think what we can make progress on is making writing that specification easier. And that's exactly what this like SMT model checker does. Is most programmers are already used to putting assertions in their code, for example, that they want things to abort. Basically, they're in their mind, what it means is I want things to abort if this assertion is ever met, right? But if you instead change the interpretation of the assertion and say this assertion should never be met, then you can check statically, okay, is the assertion ever reachable? And if it's not, then you can just remove the code that handles that assertion from the resulting binary that you produce. So I think that same sort of incremental approach, like one example of a tool we're developing kind of internally is what we call like a symbolic property testing tool. So if you've ever used a tool like Quick Check or Hypothesis for Python, which lets you write down property tests and then it randomly tests it with a bunch of different values and sees if it can find any counterexamples to your property. We're doing that, except we actually symbolically execute the program and verify that the property holds on all executions, not on a bunch of random executions. So this is an example of a tool that I think once we've refined it and released it for more people than just our internal developers and our auditors, because right now it's got a lot of rough edges and we don't want to like, release a tool with a lot of rough edges. This is the type of thing that would make it easier for you to say, okay, I want to take Uniswap. I want to add some gadget to Uniswap that, makes it more profitable for liquidity pool providers or something like that. That's a hint. I want someone to do that. Then you can write your own property tests in Solidity in the same testing framework you're used to writing them, hit the button, and maybe the verifier is able to say, yes, your property tests were verified and your new specification holds against the code. So I don't think we can get rid of this process of having to write the specification, because inherently that's a human intention thing, right? But we can make the process of, okay, writing the specification is easier and checking that the specification meets the code is automated. Those are the two things I think we can make progress on.
Absolutely. We have to wrap up, but I can easily see this is the theme, the paradox, if not a dilemma. So let me say it again. For Drill, is really having the privacy in the public blockchain, right? Dionysis is going crazier, keyless, to doing all this encryption and actually dealing with the economic security versus of computation that are like valuable. And then the last part that Everett touched on, do we want to put software out there that people can fork? And the whole idea of smart contract are composable, right? All this data and contract call can be called by anyone outside, and anyone can steal it and use it and call it without knowing the precise specification. It's actually a paradox of what we are writing software and security and stakes in the public blockchain with concurrently running by everyone. I don't know whether you guys have another hour to hang out here, but I would love you guys to leave a question, so that maybe we'll follow up with you like one-on-one between you guys. Maybe we'll meet again in a few months, in a year, that I'll remember this is the question you ask of all of us. Drew, you want to start?
Is this what's the topic?
Just ask a question or bring up a topic, some controversial thing that you want to like.
Ooh, I don't know.
So maybe I'll follow up with you. So that
I'm super interested in this time lock encryption stuff. Primarily, I'm interested. It seems very easy. So I want to play devil's advocate a bit. It seems like a bad user experience if the user has to actually spend their money in intervals of time, or else someone else is going to be able to spend their money. But one way I was thinking, this sounds very architecturally similar to some of the things we're building at Webb. But what if you, prior to putting the data on IPFS, you hashed it, and you require that the time lock encryption is of hashed data, and the user needs to submit a proof of knowledge of the pre-image once it gets decrypted in that later date. That way you get around at least someone being able to steal the money, but preventing the person from spending it on these intervals. And it's very interesting. I think this is very paramount to what we're trying to do at Webb, is kind of identify and develop the following case study, which is, can we build a mechanism like you mentioned, Dionysis, where we resolve the system across a chain? So maybe this Merkle root is on Ethereum, but I'm able to prove that I can decrypt it on Harmony and spend the money on Harmony, maybe through some bridge mechanism. So we'll see. Hopefully these sorts of primitives get built out. I'd be really interested to follow up and hear your thoughts on what the timeline is, you think, for application.
Yeah, absolutely. And regarding your question about, hashing things and people being able to spend earlier, I will send you my paper, and you can read all the details there, because I think we have to wrap it up. But these are very, very interesting questions, and they're central in the treatment in the paper, exactly what you're asking, right? So I think you'll find all your answers there. And my question, to answer what Stephen was trying to say regarding this witness encryption scheme, is when witness encryption, right? When will we have this? And this is my question to my colleagues who are experts in Lattice encryption, because this is not my area of expertise and I cannot develop it. I mean, this needs a separate PhD in a completely different field of cryptography. But hopefully, someone in the Lattice field will maybe hear this and figure out that there's many very practical applications in this in the space of blockchain. Hopefully this will drive some of the innovation there and reinvigorate that. And so my question that I would like to hear maybe the answer next year is, when are we going to have a practical witness encryption that we can use for time lock encryption application?
Absolutely. Everett?
Yeah. Okay. So take my questions with a grain of salt, because I'm very ignorant about the zero knowledge and this sort of world. But I also have a when question, which is, when will an average Solidity developer be able to have access to these privacy components that are being developed? Because I know that there's a lot of advanced research in zero knowledge. I don't know much about it, but I know it exists, and I know that almost no one is using it, right? So what is that barrier to entry for using it? Is it the programming languages are not accessible? Is it that you have to know a bunch of math theory to even begin to working with the tools that can do this for you? So from my perspective, I want to know, what is it going to look like from a Solidity programmer's developer? That way I can start making semantics for it and start doing verification over stuff like that. But I also want to know, I gave up long ago on having privacy in anything blockchain, basically. I just accepted, okay, everyone can see where all my money is, right? Am I going to be able to kind of revive that dream in the near future without having to use exotic or esoteric platforms? So there's my challenge to you guys.
Wow, thank you all. This is easily my favorite panel that I've hosted and been to. Most of all, I want to bring out the message, right, for all the audience anyway, is come in the space, right? It's not just about blockchain, it's not just about a currency, but whether you're dealing with compilers, building a product on privacy, figuring out the math, the lattice field and number theory is easily the queen of mathematics and science. That was my master in undergrad, right? I just can't believe someone would say, let's make that work so that we can have a product that our user can use. Same thing, I always tell my team that once we have done all the mainnet and stuff, I'll get back to design programming language, so that my kids they don't need to learn Solidity or JavaScript in order to do anything with the computers. And the last one with Drill, really thinking very hard about practical engineering and product that actually will be used by everyone, is why also being a startup entrepreneur in Silicon Valley guy, that product market fit is right now, right? Anything you do, people are waiting for you to build a practical wallet, practical smart contract compiler, checker, that hopefully all these discussions will bring more talent and more collaboration across different fields. Yeah, well, thank you, everyone. Yeah, thanks for the time today. Can't wait to follow up. Yeah.
Thanks.
Stephen, thank you so much for bringing us together. It was wonderful.
Absolutely, such a pleasure.
It was an honor to speak to these experts in fields that I have little knowledge of, and I hope we get the chance to speak again very, very soon. These panels are super interesting and informative. I've already collected many unknown words and phrases that I want to look up over the next few days from what I heard today.
Same here. Let's follow up in the email and in the discussion. Thank you again. Have a great day, guys.
Bye, everyone.
Have a great day. Bye.